All right, so this is 2019 FRQ number 6. It says functions f, g, and h are twice differentiable functions with g of 2 equals h of 2 equals 4. The line y equals 4 plus 2/3 x minus 2 is tangent to both the graph of g at x equals 2 and the graph of h at x equals 2. So it's tangent to both of them, both g and h. All right, so find h prime of 2. So this one is actually pretty good. H prime 2, what is the slope? What is the derivative at 2? Well, it should be the same as the tangent line slope at 2. So since this line is tangent to h at x equals 2, then h prime of 2 is the same as that slope. So it's the same as 2/3. All right, that one's straightforward. Okay, let part B, let a be the function given by a of x equals 3x cubed, h of x. Write an expression for a prime and find a prime of 2. Okay, so I'm going to use this space up here. B, so a of x is defined as this product. So to find a prime, you're going to have to use product rule. So a prime of x equals the derivative of 3x cubed. So that's 9x squared times h of x plus 3x cubed h prime of x. Okay, now we're looking for a prime of 2. So plug in 2. So 9 times 2 squared h of 2 plus 3 times 2 cubed h prime of 2. All right, so what does that give me? 9 times 4 is 36 times h of 2. Well, it says h of 2 equals 4 plus 3 times 8. 3 times 8 is 24 times h prime of 2, which we got from part A. That's 2/3, right? So multiplying this out, I get 144 plus 16. So I get 160 as my a prime of 2. Okay. All right, this next one's a little bit rougher, so let's see if I can explain this slowly. All right, the function h satisfies that h is equal to this defined for x not equal to 2. It is known that the limit as x approaches 2 of h of x can be evaluated using L'Hopital's rule. Okay, so we're going to have to use L'Hopital's rule somehow. Using limit as x approaches 2 of h of x to find f of 2 and f prime of 2. Show the work that leads to your answer. Okay, so let's see. Let's start with part C here. So first of all, we know that h is twice differentiable. It says right here, h is twice differentiable. If it's differentiable, it is continuous, right? If it's continuous, not necessarily differentiable, but if it's differentiable, we know it's continuous, which is great. So we know h is differentiable. What does that imply? That implies h is continuous. What does continuity mean? Well, continuous in this case means that limit as x approaches 2 of h of x will equal to h of 2, right? The limit will equal to the value, which is equal to 4, right? Again, that's what is given to us here in the given of the problem. Okay, so that means then if we look at the limit as x approaches 2, so we're going to define this, right, using this right here. So limit as x approaches 2 of h of x, that's limit as h approaches 2 of x squared minus 4 over 1 minus f of x cubed, right? So we know then that from what we defined here, this limit is equal to 4. So that means this is equal to 4. Okay, so looking at what we have right now, to satisfy the L'Hopital's rule, remember the condition of L'Hopital's rule says we need to get an indeterminate form, we need to get 0 over 0. Well, if you plug in the 2 into the numerator, you will get 2 squared minus 4, which gives you 0, right? So that already gives you 0. Now I need the bottom to also equal 0 to satisfy the L'Hopital's rule. It already says we got to use L'Hopital's rule, so we have to make sure the bottom is also creating that condition that happens, right? So now you're going to say 1 minus f of f of 2, oops, too many f's, sorry, try that again. Let's do the denominator. So 1 minus f of 2 cubed must equal 0. And why f of 2? Because my x is approaching 2, right? X is approaching 2. So that means then f of 2 cubed equals 1. Cube root both sides. F of 2 equals 1. Oh, okay, so I already found f of 2. That's what the first thing tells me to do. I found f of 2. Yay, one part done. Okay, now continuing with this, it says f up here is differentiable. So keep that in mind. So if f, same idea that we use, if f is differentiable, it is continuous, which means limit as x approaches 2 of f of x will equal to f of 2, and we just defined that, that's equal to 1. All right, perfect. All right, so we're gonna go back to the original limit there. So going back to the original, it's a little convoluted, so we're gonna go back to this original limit here. So limit as x approaches 2 of x squared minus 4 over 1 minus f of x cubed, right? And we said, we plug it in and we get the condition of L'Hopital's rule. We get 0 over 0. Okay, so now that we have the condition of L'Hopital's rule satisfied, we can now go ahead and use L'Hopital's rule to solve for this limit, right? So go ahead and now take limit as x approaches 2, take derivative top. The bottom, the 1 is a constant, so bring down the negative, and 3 f of x squared f prime of x, right? Okay, plug in the 2 because that's what we're supposed to do with limits. So 2 times 2, negative 3 f of 2 squared f prime of 2. All right, I get 4 over negative 3. F of 2 is 1 based on here. So 1 squared f prime of 2. So I get 4 over negative 3 times f prime of 2. Now, we know this limit is equal to, right here it says equal to 4. So this is equal to 4 over 1. So that way 4 equals 4 on top. So I can go ahead and just look at the bottom. Negative 3 f prime of 2 equals 1. So f prime of 2 is equal to negative 1/3. And that's it for this problem. So again, it's a little convoluted. It goes, backwards and forwards using the same equation over and over again, a little bit like related rates. That's all I'm going to say. Okay, last one, D. It is known that g of x is less than h of x for between 1 to 3. Let k be a function satisfying that k is between g and h. So this is a sandwich or squeeze theorem where you got one on the left, on the right, you got a this inequality. So k is going to be between g and h, right? So whatever g and h is defined as, right? And so k is continuous. Is k continuous at 2? Okay, so let's see. We know that h, g, and h are differentiable, right? Up here says g and h are twice differentiable, so great. So to go with part D, we are on, let's see, g and h. All right, so we know that g of x and k of, no, not k, h of x, not k yet, all right? And, okay, h of x are differentiable. What that means then is g of x and k of x are continuous at x equals 2. So what does that mean? It is defined then that limit as x approaches 2 of g of x is equal to g of 2, which I know in the beginning it says g of 2 is equal to 4, okay? And then same thing, limit as x approaches 2 of h of x is equal to h of 2. All right, so let's take a look. Limit as x approaches 2 of h of x. Again, we're using this again. It's right here. Oh, sorry, this is terrible. Let me box it out. It's equal to 4 again, right? So that's equal to 4. So then if g is sandwiching the k, then this limit is equal to, right, this is equal to 4. This is 2. Sorry, so we know then that g of 2, right, because we know the functions are defined this way. And we also know g of 2 is equal to 4, and this is equal to 4. So you have 4 less than equal to k of 2. That's going to be 4. So the only way this can be true is k of 2 is equal to 4, right? And so if k of 2 is equal to 4, and then also we can look at the limit too. So limit as x approaches 2 of g of x sandwiches limit as x approaches 2 of k of x sandwiches limit of x approaches 2 of h of x. Well, these are equal to 4. This is also equal to 4. So again, for this to work, limit as x approaches 2 of k of x is also equal to 4. So based on this condition, k is continuous at x equals 2 because the limit and the value are exactly the same. Therefore, it is continuous at x equals 2. Okay, that's it.